this while we're on this together.
I can work on our process book too. I needed like
Congratulations on the award.
Yeah, thank you.
Especially because like, I think about Thursday, rent out a server for AWS.
or Friday.
Even on AWS.
Yeah, I have like, I
around like DC version or two of those components that
their projects.
Alright. Okay, folks, let's get started. So, I hope you had a wonderful Thanksgiving holiday break. And now it's back to reality. The reality is we need to finish the discussion on transaction and get ready for the final test on Tuesday. Okay. And so I will pick up from where we left right before the break. We were talking about concurrency control for transactions. We talked about log-based approach. I will give you a quick recap of what we said here, right? So for the log-based approach, the database kernel introduces two types of logs on objects. An object can be a table, can be a row of a table, can be even can be as small as a single value. If you define a view that narrow down to that value, you can log that view. Okay. There are two types of logs database system had introduced. One is shared log, denoted as S. The other is exclusive log, denoted as X, exclusive log. So this is what we call the log compatibility matrix or log compatibility table. If you have an object having a shared log on that object, it doesn't prevent other transactions from acquiring another shared log on the same object. Okay? So a shared log is compatible with another shared log. However, a shared log is not compatible with exclusive log. Meaning, if some transaction had already acquired a shared log on a given object, later on another transaction comes in and asks for an exclusive log on the same object, the second request will have to be blocked and wait until the release of the shared log by the first transaction. Of course, all this discussion happened with respect to the same object. A shared log on object B has nothing to do with either a share or exclusive log on object B. Does that make sense? Finally, an exclusive log obviously is not compatible with another exclusive log. So the whole idea is that you want to acquire a shared log for any objects that you want to perform a read operation over. The simple idea behind this is that while you're reading the value of this object, you want to prevent others from changing the value of this object. Okay? This actually gets rid of, if you think about it, this gets rid of dirty read problem. Because what is a dirty read? Dirty read means that you're reading an uncommitted write by another transaction on the same object. But if it's an uncommitted write, which basically implies that first transaction must still have an exclusive log on the object, which will prevent you from acquiring a shared log in the first place. So you cannot possibly read that dirty item. Does that make sense? To give you an example how elevate the dirty read problem. Using those two types of logs, people introduce two locking protocols. The first one is what we call straight two-phase locking protocol, or straight 2PL. The idea is, essentially what I said just now, you acquire exclusive log for any write you want to do and shared log on any read operation you want to perform. And finally, you only release logs, all of the logs you have. You release all of them at once at the time you are ready to commit or abort. You don't release log anytime sooner than that. Okay, that's what we call straight two-phase locking. So if you look at the top figure here, where the y-axis denotes the number of logs you have acquired and hold over the course of executing this particular transaction, one transaction. And x-axis is time. For straight two-phase locking, if you think about it, the picture looks like this. You slowly acquire more and more logs until you reach a point where you no longer need any new logs. You acquire shared log on all the objects you want to read, you acquire exclusive log on all the objects you try to write. So it reaches a peak moment after which you acquire no new logs. Okay? And in between, from here to here, and also afterwards, you do whatever your business logic requires you to do within your transaction. For example, do some calculation, add up A and B, write to C. Those are what we call business logic of your transaction. Those take place during the phase of acquiring logs as well as after you have acquired all the logs. The point is, the number of logs you hold as a transaction will immediately drop to 0 at what point? For straight two-phase locking, it drops to 0, meaning you release all your logs at the time you commit or abort. Any question regarding to this figure? Now that being said, what about the non-straight two-phase locking? The non-straight two-phase locking variant is very similar to straight two-phase locking, except it allows you to release log a little bit sooner if you would like to. In particular, you can start releasing logs if, that's a big if you know you're not going to acquire any new logs. Not necessarily just another log on the same object, but any log on any object. If you know you're not going to acquire any log on any object, you are allowed to release any existing logs you hold. Question over there.
Would upgrading from I guess a shared block to an exclusive block, would that count as acquiring a block?
That's considered as acquiring a new lock. It is a new lock, right? Because you had a shared lock, you want to upgrade it to an exclusive lock, that's considered a new lock. Which means if you are thinking about upgrading a lock you have, then before you do that, you cannot release any lock, even in non-straight to face lock. Any question on this? So the picture, if you compare straight to face locking with non-straight to face locking, it actually looks like this. This is essentially the picture for non-straight to face locking, which is there's a phase where you acquire locks. Then there's a phase you hold on to all the locks you have. Then you slowly start releasing locks. But you notice one thing, which is at this region, when the number of locks goes down, what happens? Once it starts go down, can it go up? It can never go up. It has to go down. Actually, to be precise, if you look at over time, this actually, to be precise, should be a staircase curve. Something like that. You have this number of locks, you start releasing some of the locks, then you stop releasing for the number of locks, so this will be flat for a little bit, then start going down again. Does that make sense? So it should be a kind of a staircase curve. Same goes for the acquiring lock phase, right? The picture shows the general trend going up, but in reality it's really a staircase curve. Like that. Meaning it's not necessary for you to acquire all the locks at once. You acquire some locks, you start doing some business logic, you acquire new locks, and do something. Question over there?
So when you start releasing them, you cannot acquire it anymore.
Yeah, that's right. That's why you can never have things like this. That make sense?
So how would you know if you were writing like this in like a real database? I'm just imagining what kind of workflow would you be like allowed to start releasing locks? Because I feel like how would it know that I'm never going to want that thing again, or that I'm not going to need any locks?
For ad hoc workloads, where the operation you do is determine on the fly what you said is true. But for most transactional workloads, if you look at real database systems, like take banking, for example, banking transaction as example, right? Typically, what you do is you submit transaction to the backend database when users have specified all the action fields you want to do. At that point, you know exactly what business logic you have within a transaction, right? So you kind of know your workload ahead of time.
So it'd be like a stored procedure or something?
Yes, stored procedure, yeah. Okay, so the final point I'd like to make is both straight-to-face locking and non-straight-to-face locking permit only serializable scaling. What is serializable scaling? We talked about this right before Thanksgiving. I hope you, big Thanksgiving dinner, didn't make you forget everything we talked about before Thanksgiving. So what is a serializable scaling? Can someone tell me that? Go ahead.
If you interweave the transactions, it's effectively the same as if you did them sequentially.
Exactly. A serializable schedule says if you have a schedule that interleaves actions from different transactions, that's allowed as long as the end effect is equivalent to one of the serial schedules you have. Given n transaction, you will have n factorial number of serial orders of executing them. A serializable schedule is one that is equivalent to one of this. It doesn't really matter which one you are equivalent to. Note that the effect of these n factorial combinations might be totally different. The effect of doing T1 and T2 could be different from T2 than T1, but they could be the same as well. It really depends on the business logic embedded within T1 and T2 respectively. But the point is, if you start interleaving them, it's okay as long as the end effect is equivalent to one of the serial execution of these transactions. And that's what we call the serializable schedule, and which is also the strongest isolation level we talk about, right? We talk about serializable isolation level. We also talk about, what's the other isolation level we talk about? Repeatable rate isolation level, right? However, I'd like to highlight an important point, which is, okay, both straight two-phase locking and non-straight two-phase locking permit only serializable schedule, meaning that if you implement your database kernel, which you will be doing in your lab 5, using straight two-phase locking or non-straight two-phase locking, you end up with only serializable schedules. Does that make sense? But this does not mean all serializable schedules will be allowed by straight two-phase locking or non-straight two-phase locking. Does that make sense? Yes or no? These two are not equivalent. Those two statements I just said is not the same. Okay, something only allow serializable schedules to be produced is not to say all serializable schedule will be passed. We will be able to pass the check of straight or non-straight two-phase locking. Yes or no? For example, I'll give you another somewhat similar analogy to this. Let's say we have a car manufacturer company and I have a production line. I say my production line only produce sedan cars, small four-door cars, passenger cars coming out of my production line, okay? This is not equivalent to say all sedan cars can be produced by my production line. These two are different. Does that make sense? Okay? So straight and non-straight two-phase locking only produce serializable schedule, but doesn't mean all serializable schedule will be able to pass the check of straight or non-straight two-phase locking. But that's okay. Because at the end of the day, our database system is responsible for producing a schedule rather than checking a given schedule. You are responsible to produce a valid schedule rather than, given multiple schedules, select which one is valid. Does that make sense? So that's kind of point number 1 I'd like to make. Point number 2. What's the difference between straight and non-straight two-phase locking? I think towards the end of last lecture, I showed you an example where straight two-phase locking will prevent the execution of that transaction, where non-straight two-phase locking actually will allow that particular schedule to move forward. We have plenty of such examples in your homework file, actually. So you wonder, why don't we just always use non-straight two-phase locking? Since both of them produce serializable schedules and non-straight two-phase locking allow more level of interleaving actions of transactions because of the early release of locks, why not we just always go with non-straight two-phase locking? Why bother with straight two-phase locking? Well, a fundamental drawback of non-straight two-phase locking is that it allows cascading abort to exist. It allows cascading abort to exist. Meaning, if you release a log too early, then somebody else may acquire that log. Actually, I could give you a perfect example of that. I think we talked about this toward the end of last lecture, right? So suppose I get a share log, okay, exclude log on C. You see, at this point, let's say I'm trying to read B, so I'm going to acquire share log B. Because of this, I will be blocked. Does that make sense? So you cannot proceed. So for non-straight two-phase locking, what I will do is after acquiring the exclusive lock on C, what can I do? I know I don't need, and after finish writing B, I know I don't have to acquire any new locks. I can start release locks. Right? And so that I can proceed. right? Because now I can occur that shared. Now you are running to C object. The reason, if you compare this versus straight through face locking, for straight through face locking, what happens? Can you do this now? For straight through face locking, you cannot do this. You can only release lock after you finish writing C and you commit, which means this will be blocked all the way down here. And if writing C, this object C is an expensive operation, let's say the big object, take quite some time, you can clearly see this approach is much better than the straight to face locking approach. That make sense? But what's the potential downside of this if you do this? Can someone tell me? A potential downside is, go ahead.
Somebody might try B.
Somebody might?
Might, like T1.
T1.
Might try B, right?
So let's say I'm just reading the value of B. I'm not writing B.
Oh. But it's not committed here.
It's not. That's the key. Yeah. B. The value of B is not committed yet. And what's wrong with that?
So if you release the lock on B, T1 like so reads B, it's all good. If T2 commits, then it's okay.
Yes.
But if T2 aborts,
Exactly.
then T1 is like invalid.
Yes, exactly. If T2 commits, then everybody is happy. You get better efficiency compared to straight to face locking. Everything is perfect. Okay. But what if T2 come back and says, in the writing of C, something goes wrong, and I decide to abort. And because of that, the value of B read by T1 now becomes invalid. So I have to abort as well. But unlike the abort of T2, this is a forced abort. Meaning it's not in T1's interest to abort, but I'm forced to abort. And this is what we call cascading abort. And if I can construct this example using a chain of transactions, in the worst case, that the abort of one transaction will cause thousands and tens of thousands of other transactions to abort, in the worst case.
Do you also, I guess, then have to, I don't know, I guess you kind of seems like you need to also keep track of like some additional information, since obviously before T1 can't be allowed to commit until T2 commits, right? Because you don't know whether T1 could be invalidated. If you allow this, right?
Exactly. So I say, so
Or I guess
the point is, what if we allow T1 to commit, and then later T2 come back and abort? That's an even more weird situation where essentially you're telling a committed transaction to abort. It's even more strange, right? From the eyes of user, right? I mean, this is not nice, but at least it's doable. It's kind of like somebody in the last phase of finishing up their transaction of buying a house. You come in and said, sorry, this deal has to go back because your neighbor decided not to sell his house. It's kind of bad news, but because I haven't signed the contract, it doesn't feel as bad. This is like, I signed the contract, everything is approved by the bank, and you come in, you tell me, well, because your neighbor decided not to sell his or her house, even you have a signed contract, but throw that down your toilet and flush it away. Nothing is done. Right? That's really, really weird. Right? So yes, Gilly is right. If you want to prevent the abort of a committed transaction, you have to do additional bookkeeping to so that using non-straight to face locking. Of course, this is the worst case scenario. What happens if this guy commit? Then everything's fine. Doesn't really matter whether you commit here or commit there. But to cater for that worst case scenario, you basically do not allow this guy to commit until the other guy has committed. But then this means additional bookkeeping. Yeah. That makes sense? So that's essentially all the discussion I want to have for straight to face locking and non-straight to face locking. Aborting a transaction is easy, so I will skip this part. You can just read this yourself. Basically, you go back and you undo the effect of this. You undo the effect of this. This brings up an interesting question: is okay. If you think about if I abort here, I haven't done anything with regard to object C, so I don't have to do anything with regard to that. But I do need to undo the effect of this. How am I supposed to do this? Suppose the original value of B is 10, and now I update this B to 15. If I simply overwrite this value of B over that, there's no way you can undo the effect of this, because there's no way you know what the value was. That makes sense? Before you applied the update operation. So this brings up an interesting challenge, which is how do you undo the effect of a transaction? The idea is to use log. I'm gonna have a dedicated discussion on this later on. So for now, I will just skip this particular slide. We'll come back and visit this in detail. Okay. Next, I'm gonna introduce something called conflict serializable schedules. So we say two schedules are conflict equivalent if they involve the same actions of the same transactions, and every pair of conflicting actions is ordered the same way. What do I mean by conflicting actions? Conflicting actions refer to those three anomalies we talked about earlier in last lecture, which is read and write, write and wait, and write and write. Those are the three types of conflicting pairs of actions we talk about. Of course, they all refer to actions from different transactions. From the same transaction, they never conflict with each other. So conflict serializable basically says you have two schedules, okay, involving the same set of actions from the same set of transactions. That's requirement number one. Requirement number two, you identify all potentially conflicting pairs of actions from any two transactions. And if in schedule 1, action 1 precedes action 2, then in schedule 2, it must be also action 1 precedes action 2. Here, let me clarify what I mean by precede action 2. It does not mean action 1 is immediately followed by action 2. It only means action 1 happened sometime before action 2 takes place. And the gap between them can be different in two schedules. Meaning, for example, in schedule 1, I have action 1 from transaction 1, and then I have some other action from transaction 2, and action 2 from transaction 3. And suppose action 1 and action 3 are the conflicting pair of actions. Okay, where in schedule 2, I have action 1 from transaction 1 immediately followed by action 2 from transaction 3 with nothing in between. Still, that's considered conflict equivalent because they are ordered the same way. It's just a relative ordering of the two. It doesn't really matter what happens in between them. Are you all clear on this point? Okay. Of course, the example I gave you only talk about one pair of conflicting actions. You may potentially have multiple such conflicting pairs of actions, and each pair needs to be ordered the same way in order for the two schedules to be considered what we call conflict equivalent. Okay? That's all it says. Now, once you understand conflict equivalence, you should be able to understand the next concept, which is called conflict serializable. Conflict serializable is a special kind of serializable schedule. It's a subset of serializable schedule. So imagine this is the set of serializable schedule. Okay? Of course, given I have this set only makes sense if you are given a set of transactions. Let's say T1 to Tn. Suppose I have once you are given a transaction, it defines a set of serializable schedules. Do you all follow me? So this is essentially the picture here. Draw this as a big set. And conflict serializable schedules conflict serializable schedules is a subset of schedules from the set of all serializable schedules. That's all it says. And conflict serializable schedules refer to those schedules that are conflict equivalent to one of the serial execution of these transactions. Does that make sense? In other words, among the serializable schedules, I have another subset, n factorial of them, which refer to serial execution of T1 and Tn, right? They themselves obviously are serializable schedules because it's serial execution of them, and we have n factorial of them. What is the conflict serializable schedules? Anything here is equivalent to this using this concept of conflict equivalence. That's essentially the set of conflict serializable schedules. Is that all? Is that all clear? The question next is how do you identify, how do you check if a given schedule is conflict serializable or not? And this actually provides a useful way for you to check if somebody produces a schedule for you, whether it is a serializable schedule or not. Because if it is conflict serializable, it must be serializable. Of course, to be a little bit careful, right? If something is not conflict serializable, it does not necessarily mean it's not serializable. So it's a sufficient condition, but not a necessary condition. How do you check this? Well, you build something called dependency graph. You build something called dependency graph. The idea is you draw a node to represent each transaction. So for here I have two transactions, so I introduce two nodes, T1 and T2. Then I draw a line from one node to another, a directed line. It's a directed arrow line. If there is a pair of conflicting actions involving an object between the two transactions, and the arrow points to the transaction that has the latter action from the pair of conflicting actions. Okay, let me illustrate this using this object A. So I have write A, then I have read A. So I have a write and read conflicting pair of actions, and that read A happens after the write A of T1. That's why I have an arrow coming from T1 towards T2 with write to object A. Is that clear? Similarly, why there is an arrow going from T to T1 on B, that's because there is a write and read conflict. And in addition, there is also a write and write conflict involving B, and T1 happens, the action from T1 happens after the action from T2. That's why the arrow goes the other way. And this is what we call the dependency bar. The dependency bar. And a theorem you can use to check for conflict serializable is the following, which is if your dependency graph is acyclic, then it is conflict serializable. Acyclic means there's no cycle in it. Otherwise, if your dependency graph has a cycle in it, doesn't matter how many cycles you have. You may have multiple cycles actually. As long as you have at least one cycle, then it is not conflict serializable. Is that clear? This brings up another interesting challenge, less relevant to this course, but an interesting problem in practice. Given a large graph, in practice you may have many, many transactions. Given a large graph, how do you quickly detect if there is a cycle in it at all? For example, suppose each of you is a node, and imagine I connect you if you are a friend on Facebook. There are these imaginary lines on my brain now, and without I know I'm friend with Julia, so there's a line between us. I want to check if there's a graph. Is a cycle on this graph. What does cycle reveal? Cycle reveal that you have a close friendship embedded on this graph, right? So I'm friend with him, and he's friend with her, and she's in turn friend with me. And this has a lot of application practice. For example, banks detect cycle all the time. Why they detect cycles? For money laundering, to detect money laundering operations. In money laundering, what do? They typically say, okay, I have money, I transfer to person A transfer to person B, back to C, back to E, back to F, eventually it goes back to me. So that I don't want government to track where the money goes. So typically if there's a cycle going on, that means something is wrong. Because you're basically washing your money, essentially. Okay? So that's why detecting cycle on a large graph is an interesting and important problem. Okay, that's how you check the conflict serializable. So we're gonna skip the pure serializability discussion. So skip this. I don't require you to understand this. So next, I'm gonna talk about deadlocks. For any locking protocol, once you have locks in place, you may potentially end up with something called deadlock. I'll give you a simple example of this. Suppose I'm pair lock of A. Okay. While you are doing this, T2 says I'm going to occur the lock of B in parallel. And I'm going to repeat, there is no conflict whatsoever. This is totally okay. And now I'm going to try to write B. So I'm going to occur. So I'm trying to do this. And this guy say I'm trying to so that I can do it right away. What's the problem? Well, this operation is impossible because of that. And this operation is impossible because of this. Do you see what's going on? And suppose you are using straight two-phase locking. And what's wrong with this? Straight two-phase locking says they can only release lock when they are ready to commit. For T1, he will say, okay, I'm not ready to commit. I haven't finished writing on B. For T2, she says, I'm not ready to commit either. I need to write A. Right? So what happens now? Well, it's interesting to see what our government will do, right? There's a shutdown, potential shutdown coming into picture, right? Do you follow the politics at all? Nancy Pelosi, what's this guy? What's this senator name? Nancy. And they are supposed to meet Donald Trump this afternoon, and Donald Trump went on Twitter says, no deal with Democrats. So they canceled the meeting with Trump this afternoon. Right? That's essentially what's going on here, right? So essentially this guy says, oh, you should release your law. Why not you release your law first? If nobody compromised, then nothing can be done. That's what we call deadlock. So obviously you cannot have a database system like this. You have to do something about it. And there are two ways to address this issue. One is deadlock prevention. The other is called deadlock detection. So let me explain both of them. So deadlock prevention says, I gotta take a passive approach, meaning I'm not actively trying to produce schedules that will not lead to deadlocks. Passive approach means I will wait and observe until there is a deadlock being produced. Then at that point I will do something about it. So that's what we call deadlock prevention. And deadlock prevention, the idea is very simple. You assign priority based on timestamps. The timestamp of the start timestamp. Start timestamp. Whoever starts earlier will have a higher priority. So luckily we're dealing with database deadlocks. That's easier to address. If you try to tell senators in Washington DC said, oh, you have a higher priority just because you arrived DC earlier, that obviously not going to work, right? So, but for database transaction, we can impose this rule. If you start early, you have a higher priority. So once we detect there's a deadlock, what do we do? Once we detect there's a deadlock, whoever has lower priority has to abort. So suppose T1 starts first and T2 starts later. So in this case, T2 will be forced to abort. Once you are ready to abort, what happens? You will have to release this log on B so that I can proceed. You see, that solves the problem because once I proceed, I release all the logs. When you come back, you will have no problem acquiring both logs and proceed. Right? However, there's a big if. If what? If when you come back and try to do this again, there's not another guy like T1 come in and do the same to you. And then you may be forced to be aborted again. So you don't have to see that happen, right? So this is what we call starvation. So you force a transaction to abort and he or she come back, and the same situation may arise again. So the idea is if a transaction is forced to abort because of deadlock prevention, when the transaction comes back into the system again, you assign its priority based on its original timestamp rather than the new timestamp it starts again. That way, eventually, this transaction will have the highest priority in the system. Otherwise, this transaction will always have a lower priority compared to others, and will always be aborted. That make sense? Okay, so that's deadlock prevention. Yes?
Wait, so with wound weight, I'm so confused. So that
I mean the two different policies under this. Okay.
Yeah, so I guess weight die kind of makes sense. It's like, yeah, just abort it if you can't fix it. But wound weight, like when would you not be able to abort TJ?
When would you not?
Yeah, if TI has higher priority.
If TI has higher priority, TJ will abort immediately.
Okay. So when would TI have to wait and then
if TI has lower priority.
Oh, okay.
Now, deadlock detection takes an active approach. Active approach means that I want to make sure there is no deadlock to begin with. And for this, we have to, again, use graph theory to help us. We'll produce something called wait for graph. Meaning that when system produce a schedule, and before you go ahead and execute transactions, based off that schedule, you check whether there is a deadlock potentially exists for that schedule. Okay? And the way you check that is to produce a wait for graph based on your schedule. So those are transactions. And there is an edge. This is very similar to the concept we talked about, the dependency graph we just talked about. The idea here is that if there is an edge, if TI is waiting for TJ to release a log for your schedule, for example, suppose this is the schedule I produced, and you realize T2 will have to wait for T1. If you draw this on a graph, T1 and T2, you see T1 has to wait for T2 because of this, and T2 has to wait for T1 because of that. And this is what we call a wait for graph. Again, if there's a cycle in a wait for graph, what does it imply? That implies your schedule has a deadlock. and you have to reschedule this. Okay, so that's essentially the idea. There are some examples of this. I will ask you to read this example. Okay. There are some other things we have glossed over, and I'm not going to dive into the detail of that, and those are not required for the final test anyway. So that's essentially everything you need to know about concurrency control. To quickly recap, you need to understand what is different isolation levels, what is serializable isolation level, what's repeatable rate isolation level, what is the log-based approach as a concurrency control mechanism to satisfy a particular isolation level, and what is straight-to-phase locking, non-straight-to-phase locking, conflict serializable, what is dependency graph, what's wait-for graph, what's step of detection, and what's step of prevention. Those are basically all the concepts you need to know, and you will implement some of those concepts in your lab 5. Is that clear? Next, we're going to talk about something else. Another very interesting topic. Now, let's consider going back to the properties of transaction. What are the properties of transaction we need? We need ACID, acid. What's A? Atomicity, what's C? Consistency, I? Isolation, D? Durability. Consistency is enforced as long as you have constraint checking in place. Because it basically says you want to enforce functional dependencies before and after a transaction has been executed. So as long as you have constraint checking in place, consistency is guaranteed. Isolation is taken care of by the discussion we just had. Concurrency control. But we haven't talked about these two guys. Atomicity and durability. How do we ensure atomicity and durability? That's essentially the discussion we're going to have now. And potentially that's the topic for Lab 6. But given the schedule we have, most likely I won't ask you to do that Lab 6. But there is a Lab 6 on these two. But most likely you won't end up doing that. But it is required for the final test, and it is part of your homework file. So we're going to talk about this acid atomicity and durability. So let me give you a simple example to motivate the discussion. Suppose I have 5 transactions. Very simple database system. 5 transactions. If you talk about commercial e-commerce website like Taobao.com or Amazon.com, they have millions of transactions simultaneously. We are talking about only 5 transactions. So this is really a toy example, if you may. So 5 transactions. X-axis represents the time. This blue line represents the course of executing a particular transaction from start to end. So T1 start from here and commit. So T1 is a good person, Starts early, commits early, everything is done. It's like you try to grab your Black Friday deal, you get in line early and you grab your stuff early, you know exactly what you want and you commit. T2 is like some person went into a shop on Black Friday night, grab many things, and at the end of the day, you know what, I don't really need it, put them back. So it worked. Right? That happens all the time. T3, a late person like me, wake up late, but still early enough to get things done. So I managed to commit. I know exactly what I want, I get into the system, I buy my stuff. I spend less than 5 minutes on my shopping for Black Friday. I know exactly what I want, I wake up not so early, get my stuff. I do everything online. I don't actually go to a shop, and that's too much time. I'm driving and all that. T4 is really typical, I think. Is those type of person who go into line really, really early and buy a lot of stuff. Either buy a lot of stuff or not knowing what she wants. Oh, this is good, this is good, this is good. Everything is good. right? So spend so much time until you know what? Due time is done, and you haven't committed yet, right? And T5 is another type of person, which is, you know, he wants to enjoy the deal, but too lazy to spend time on it. So really late, and try to, you know, enjoy the last bit of it, but too bad. By the time you're ready to check out, Amazon tell you this actually happens. There's an item on sale, add it to my cart, didn't check out in time. When I'm ready to check out, it says the price is no longer available. That price, that deal price is no longer available, right? So what do? Well, too bad, you have to reward. So that's essentially what happens, right? This is basically a simple example, but illustrates all possible scenarios you can think of in you know, Black Friday or Cyber Monday or Taobao's context, Double 11, right? All these holidays, you may end up with this kind of situations, and then the system needs to take care of all of this. What I mean by that, which means if I have committed, if T1 has committed, even if whether your system has crashed, your warehouse is burned down, for whatever reason, your computer is flooded, whatever, I don't care, I committed, you have to honor my request. Note that when you committed your transaction, it doesn't really mean those changes are permanently reflected in your database. Right? For example, when you place an order on Amazon.com, it doesn't mean those items you have bought will be shipped out and packaged right away. What happens if you order this and in between, you know, between you have committed your order to the time they pack and ship this item out, that warehouse is burned down because of whatever reason, I don't know. Can Amazon just come back and tell you, you know what, I'm not going to honor your order anymore? Obviously not. You want Amazon to still be able to honor your transaction, the committed transaction. Right? So that's essentially what we call durability. Once I commit, I don't care what you do, my changes must be durable to the end of the world. What about T2 and T4 and T5? Well, that's the concept of atomicity, which means that you are in the middle of doing your shopping stuff. Atomicity says either I honor everything you have done if you have committed, but if you haven't committed yet and system crash and you are forced to abort, then I need to make sure it's like nothing has happened. It's kind of like you have a shopping cart, you add those items to your shopping cart. When you are ready to check out, Amazon says those deal prices are no longer valid, you need to let go all these items. So we need to make sure everything you place the order needs to go back to the original inventory. You cannot have a partially completed order. So that's essentially the concept of atomicity in the context of transaction. You may wonder, okay, isn't T2 an easier case? T2 aborted before my system has crashed. So all the changes done by T2 should have been undone by the time system has crashed. Well, there's no guarantee of that. During this time period, if you're lucky, maybe, yes, I have finished undone all the effect of T2, but I may not have finished that yet. And maybe in the middle of, you know, I have undone this part, but this part I haven't undone yet. And system has crashed. I need to come, when the system comes back on, I need to figure out, I need to pick up from here and continue undo the effect of T2. That make sense? To make matter even worse. What about the committed guys? So for T1, most likely by the time system has crashed, because of the extended period of time, the changes made by T1 has been made permanently. You don't need to worry about T1 anymore. But for T3, you just committed right before crash, most likely some of the changes haven't been made permanently yet. For example, you place the order, 10 minutes after a warehouse burned down. most likely your atom haven't been shipped out yet. If your atom has been shipped out, warehouse burned down, earthquake, whatever, I don't care. I stuff it down the way. Right? But if it's right after it, those changes are not permanently reflected in the database yet. When you bring your system back on, again, what do you have to do? You need to make sure you need to redo these changes so that it's like has been committed. Right? So this redo and undo, all these actions, to make the matter even worse, when you are busy redoing or undoing to honor the commit and abort to ensure atomicity and durability, what may happen actually? System may crash again. This is kind of like, there's this movie called what? Inception. How many of you watched that movie? Have you watched that movie? Yeah, the movie is about you live in a reality, you live in this reality, right? It's in the real world. And there's this magic thing can force you to go to dream. So you're here, then you're one level above, you're in a dream. You are in a dream world, which is not reality, but make you think it's real. But what's really tricky about that movie is that you could be in a dream of a dream of a dream. So even if you recover from a dream, it doesn't necessarily mean you're back in reality. So the fundamental challenge in that movie is to figure out whether you are in reality or you are in a dream or nasty level of dreams. Same thing here. This is the real world, everything goes fine, and crash, one level of crash. In the middle of recovering, another level of crash, another level of crash. You need to figure out how to take care of all of that. Okay? So that's essentially what we're going to talk about next. So to continue our discussion, we'll make some assumptions. We'll assume that we have strict two-phase locking in place and updates happening in place. What do I mean by in place? In place means any write will override the original value of that space. This is different from what we call a copy on write. So for example, I have an object. This is my page. Somewhere is my record. This is a slow array. If you still remember the page organization. And I have a value here. Let's say value 10. And this is my value 8. So now I write a equal to 15. In place means I will go into this place and change this from 10 to 15. That's in place. What that means is you will lose the value of 10 forever, unless you remember this value 10 somewhere else. Copy on write means that instead of doing this, I will make a delta, what we call a delta of this, so that I remember this value has changed from 10 to 15. And this is what we also call bar type worded. So for this course, I'm not going to talk about this. We're going to assume a single version database, meaning every object in your database has a single version, the latest value of that object. And we're using in-place update. That's essentially what it says. Now, can you think of a simple scheme requiring no additional logging that ensures both atomicity and durability? Meaning that when system crash like this, there's nothing I need to do. Atomicity and durability are automatically taken care of. To understand this, we need to understand how buffer works. So buffer plays a key role in our discussion. So there are two policies we can talk about. One is called the force policy. The force policy says you want to make sure that every update is on disk before commit. example, I have a transaction. So what happened is I have a transaction. Let's see, write A and write B. Okay, what really happens when you write A, what happens? Suppose A is a particular record. This is A to B on a given page. They are not necessarily on the same page. They could be on a different page. Okay, that's a picture. When you write A, what happens? You need to write to the buffer, you need to fetch this to the database first, and you write it over it in the buffer. So there's a page of, initially it's A looks like this. This page I brought to the memory. Let me make the scale right. Now, if I write it over, this becomes, for example, change from blue color to red color, meaning that it's dirty now. That make sense? When I write B, what happens? I will take another page, initially with B. Now I will change this to red. So far so good? This is a page, this is a record on that page. Force policy says if now you're ready to commit. Force policy that says I'm not going to allow you to commit if it's like this. What's the problem? The changes you have made are only reflected in memory and not reflected on disk yet. If I allow you to commit, what may happen? Someone tell me. If I allow you to commit, now what happens? What potentially can happen?
Crash.
Yes, system crash and you lose this forever. Then durability is not guaranteed. And you need to worry about redo this, guys. Somehow. That make sense? So force policy says, okay, you can only commit if now you can commit. Okay, so that's force policy. Everybody understand this? What's the downside of this? The good news is you never need to worry about what? Durability anymore, right? Because if a transaction has committed, using the force policy, all the changes by that transaction must have been reflected by disk, which is a non-volatile permanent storage medium. You're good to go. But what's the downside of this approach? The downside of this approach is I cannot commit sooner. I have to wait until buffer manager write this stuff back to disk, which takes quite some time. And not only I cannot commit, because we're using strict locking, what happens? I have to hold on to this exclusive lock for a much longer period of time, which prevents others from moving forward. If you have many transactions, this drags down the performance significantly. To your system. Yeah, question there.
Buffer writes on the disk, but will decide not to commit.
Say again, can you repeat?
The buffer will write on disk, but will decide not to commit.
After buffer finish writing on disk, then you can commit. Only then you can commit. That's essentially what
What if
it
you
is.
decide not to commit?
If you, well, there's no point at that point. I mean, at that point, it's not you. It's the database system will basically go ahead and commit this guy. You don't have a choice. Transaction doesn't have a choice. When you finish doing what you do, what's the point? If you think about it, once a transaction finishes what he or she wants to do, you should commit immediately to release lock and resources to others. Right? There's no point of holding on to the resources anymore. So that's the force policy. It solves durability problem, but it's not good. It's no good for efficiency and scalability. Okay, I hope I can see that. What about atomicity? Atomicity is actually the somewhat exact opposite to durability. What autonomously says? That if I abort, let me go back to this picture here. I wish I close what I did just now using a transaction. I just magically say abort. It will erase all this line and all that from the end. Restore this particular state. Does that make sense? Like nothing has happened. This shows you actually one thing at least, which is undo is expensive. Yes? You follow what I'm saying? Okay. Now suppose I abort. In this case, if the picture looks like this, what happens now? Good news, you don't have to do anything. You throw away these guys from memory. You kick them out. That's it. Because the disk copy of these two records are still the original value. But what if it's like this? You abort. Now what happens? You can throw away A, and the change to A is like nothing happened. But the change to B has been reflected. And because we're using write in place, there's no way we can recover the original value of B without, of course, without using any additional information. Unless we use log and something else, we cannot recover the original value of B. Does that make sense? So this brings up a simple policy to ensure autonomy, which is no steal policy, which says, okay, the fundamental cause is that this guy, this change on B was written back to disk before a transaction is either aborted or committed. Right? You follow me? So, no steal policy says a buffer-proof frame is not allowed to overwrite a committed memory. Before the start of this transaction, whatever value on B is a committed verdict by somebody else. I don't know who committed, but it must be committed a long time ago. Some time ago. So if you try to take, this is an uncommitted verdict, because the transaction has not committed yet. If you try to take an uncommitted verdict to override a committed verdict on disk, I will reject that. I do not allow you to take an uncommitted verdict on buffer to override a committed verdict on disk. This is what we call no steal policy. If I ensure this, what happens? I never need to worry about undo any changes in the case of system crash and transaction abort. I simply throw away whatever they have in buffer, then I'm done. Okay? Do you follow me? But what's the downside of this approach? Well, eventually your buffer will fill up with these guys. And if transaction hasn't committed yet, none of them can go back. You cannot do any buffer replacement, your whole thing breaks. You follow me? Your whole thing breaks. Yeah.
I guess then you have to do something fancy when you eventually do get to the commit stage with no steal policy.
So we'll talk about what we do. Let's understand this naive policy first. But the point is, using force and no steal, we guarantee both autonomy and durability, right? If you use a combination of the two, you're done. So what's really preferred? Well, the preferred approach is to allow steal, meaning that I allow this to happen. Even if you are not committed yet, you can go and write it back. I also allow no force, meaning I allow you to commit even if you have only written this back, but the change to A is not reflected on this yet. So this shows exactly, this is still, this is no force. You can commit anytime you want. You don't have to worry about whether the changes are reflected on this or not. I will take care of that for you. It's kind of like valet parking. You leave your key there and your car is not parked yet, but you consider it's parked. How many of you like valet parking versus park yourself? How many of you like valet parking without paying a fee for it? Okay, all of you, right? Of course. So no force is like valet parking without paying a fee for it. Somebody else pays the fee for you. How nice is that? Okay? I don't know about you, I will use that service all the time instead of parking myself. Every time I go down Las Vegas, I use valet parking. Because valet parking there is free. Of course, you have to pay tip, but small price to pay. Okay? So this combination is the best one, but it complicates things. You need this picture, right? Why it complicates things? First of all, consider no force. Using no force, I committed when there were changes to a buffer that haven't made it back to this yet. What if system crash? If system crash, the changes to B is fine because it's already a non-volatile storage, but change to A is what? It's lost forever. It's lost forever because whatever in buffer is gone with system crash. And this violates durability. Using force, using steel, what if I decide to abort? Either I decide to abort or system crash. Then change to A is fine, it's gone forever, it's automatically lost. Because I haven't reflected that on this yet. But change to B, because it allowed me to steal, is already pushed to this. Somehow you need to undo this change. To change this back to blue. How do you do that? So steal and no force is the best policy, best combination to use in terms of efficiency and scalability, but it's the most complicated one to use in terms of ensuring atomicity and durability. Does that make sense? Guess what Google, Facebook, all these people are using? Of course, they use steal no force. You may wonder, oh, it's complicated to ensure undo and redo, that's why they pay you guys big money to do that. Right? They don't pay you to do force and no steal. Okay? So essentially this is the picture. We want that upper corner on the top right, which is still and no force, but then you need to worry about both undo and redo. Undo to ensure atomicity and redo to ensure durability. For example, redo to ensure that system crash, this is lost, but I still can recover this if it has committed. Undo in case it's aborted, and you allow still to change this back to the original aborted blue color. Okay? How do we, the next question, once you understand all this, I hope you do, next we need to understand how this is done. Okay? How do you do undo and redo under steal and no force? Steal and no force. Using steal and no force. And the answer to both, here's a little bit of good news, which is you don't need to have a separate operation, separate solution for undo, another separate solution for redo. You use the same solution to achieve both undo and redo with respect to steal and no force. And the answer to both of these challenges is logging. Log, you know, why people call something a log? The idea came from the logging business, right? You know what's logging business, right? You go into a deep mountain, you cut down trees, you ferry them out of deep mountain, right? And to build stuff. And if you cut down a tree, there's this, that's a tree, right? So, I don't know whether I can show you. So you see this is what we call the log of the tree, right? It documents how a tree evolves over time. Why that? Because initially the tree, the stem is the same, right? As tree grows bigger, it becomes fatter and fatter. And every year or every few years, the radius of the tree grows a little bit bigger. And it left behind these circles. One round of circle after another round of circle, right? So by looking at this, you can tell how a tree grows to the current state. Right? It documents the history of the tree. And that's why people call, whatever you read out as log for that reason. Right? You're jogging down what happened as part of your history, right? So that's the concept of log, and we use the same concept for database. And we record redo and undo information for every. So first of all, one thing that's clear: if you have read-only operations, you don't have to document them. If you have read-only operations, you don't have to document them. Why is that? Because for read-only operations, you don't have to worry about redo or undo them because they make no change to database state. So it doesn't affect either atomicity nor durability. So you only need to document update operations. And a log is an ordered list of redo and undo actions with the following format. A log record, it has a sequence of log records. And each log record has a transaction ID, a page ID, to know which page I'm affecting. Offset value, because within a page, multiple records, you have to tell me which particular record you are updating. That's the offset value. Then the length, the new value you are writing, what's the length? For example, you are updating only this part of record A, so the offset is from here to here, beginning until here, and the length is this part. Then you remember the old value and new value. This information, if you think about it, is sufficient for you to do undo and redo. Does that make sense? Okay. So that's log. I will show you, see whether I can find an example of this.
Maybe is the log, is it an entirely like on-disk data structure?
We will talk about that.
Okay.
Okay, these pictures are all very small, so anyway, you can spend some time trying to find an example of really this one. So we're gonna talk about next called this red hat logging, WAL. The red hat logging says, of course, logging is just the mechanism we use to solve the problem. If you just use logging alone, it doesn't solve the problem, right? Because the log are written on a set of pages. If you don't do nothing about that, they may get lost at the bottom. So log itself doesn't solve the problem. Log is just a mechanism we use to solve the problem. Next, we will show you how that mechanism works. So the idea is, first of all, we need to use red hat logging. WAL says the following. WAL basically boils down to two requirements. One, we must force the log record for an update before the corresponding data page gets to disk. So we are using force policy on log records. What's force policy? Force says you can only commit if the corresponding updates are already on disk. So force in terms of log says the following, which is the log record correspond to an update must have been stored on disk before that particular update can actually be reflected on disk. In other words, going back to this example here, I allow steal to happen, right? Because I allow steal to happen, even if a transaction has not committed yet, potentially this B may be written back, right? Because I allow steal to happen. This is uncommitted, but I allow you to go back to disk. However, red hat logging says, wait a minute. You cannot do this until what? Until the corresponding log record for this update is already on disk. Then you can proceed. What's the idea of this? It's actually very intuitive, right? If I do have the log record that document this update that are already on disk, even if I allow steal to happen, because this log record exists on disk, I can, if this guy is aborted later on, I can still use the log record to undo and recover the old value of B. So that's essentially the idea of red hat logging. Does that make sense? The first part of red hat logging. The second part of red hat logging says you must force all log record for a transaction before commit. Meaning all log record for a transaction must be stored on disk before the transaction can commit. Why is that? This is to ensure durability. This is to ensure redo. Because I can commit, for example, a transaction can commit because we're using no force. No force says I can commit even if some of my changes are not reflected on disk yet. But if you allow this to happen, what if system crash and lost this forever? Henceforth, in order to make sure I can redo this, I want to make sure the corresponding log record is already on disk. And this is not. So that if system crash, I lost this information forever, I can use this log record to reconstruct this new version of A that's still in memory at the time of commit. So policy 1 is to facilitate undo and atomicity. Policy 2 is to facilitate durability and redo. Together, that's what we call red hat logging. Is that clear? I stop here. I will use another 20 minutes to wrap up this on Thursday. Okay?